Welcome to Beyond the Brackets. In today's video, we'll learn how to evaluate the integrals using Cauchy's residue theorem. Cauchy's residue theorem states that if f of z is analytic on and inside a simple closed curve C except for a finite number of poles within C, then integral over C f of z dz will be equal to 2 pi I into sum of all the residues. Here comes the first question. Evaluate the given integral where C is a circle, modulus of z minus 1 is equal to 3. Comparing this with the standard form, we observe that the given circle has center 1 and radius 3. F of z is given as 2 e power z by z plus 1 whole cube. To find the poles, equate the denominator to 0. Denominator has z plus 1 whole cube. So here z is equal to minus 1 is a pole of order 3. Also, the pole lies inside the given circle. To find residue at z is equal to minus 1, since it is a pole of order 3, we have m is equal to 3 and a is equal to minus 1. Substituting these values in the formula for residue at a pole of order m and simplifying, we have 2 factorial will be equal to 2, which will get cancelled with the numerator. Z plus 1 whole cube in the numerator and in the denominator cancel out, and we are left with limit as z tends to minus 1 d square by dz square of e power z. Differentiating e power z twice with respect to z, we get e power z. Applying limit as z tends to minus 1, we get e power minus 1 or 1 by e. By residue theorem, integral over C f of z dz will be equal to 2 pi I into sum of residues inside C. So there is only one pole, z is equal to minus 1 inside C. So it will be 2 pi I into sum of residues at z is equal to minus 1. So it will be 2 pi I divided by E. For the next question, we are given the integral where C is the circle, modulus of z is equal to 3 by 2. Comparing this with the standard form, we have a circle centered at the origin with radius 3 by 2. Here f of z is given as 4 minus 3z by z into z minus 1 into z minus 2. To find the poles, equate the denominator to 0. So we get z is equal to 0, 1 and 2, which are poles of order 1 or simple poles. Of these poles, z is equal to 0 and 1 lie inside the given circle, whereas z is equal to 2 will be outside the circle. To find residue at z is equal to 0, since it is a simple pole, we get m is equal to 1 and a is equal to 0. Substituting these values in the formula for residue at a simple pole, z in the numerator and in the denominator cancel out, and we are left with limit as z tends to 0, 4 minus 3z by z minus 1 into z minus 2. Applying limit as z tends to 0, we get 4 by minus 1 into minus 2, that will be 2. To find residue at z is equal to 1, which is a simple pole, we get m is equal to 1 and a is equal to 1. Substituting this in the formula for residue at a pole of order m, we get 1 divided by 0 factorial, that will be 1. Z minus 1 in the numerator and in the denominator cancel out, and we are left with limit as z tends to 1, 4 minus 3z by z into z minus 2. Applying limit as z tends to 1, we get 4 minus 3 by 1 minus 2, so that will be simplified as minus 1. By residue theorem, integral over C f of z dz is equal to 2 pi I into sum of residues inside the given circle. So we get 2 pi I into sum of residues at z is equal to 0 and z is equal to 1. Note that here z is equal to 2 is a pole that lies outside the given circle, therefore it is not considered. Substituting the values, we have 2 pi I into residue at z is equal to 0 is 2 and at z is equal to 1 is minus 1. So the answer is 2 pi I. Let's look into the next question. Here C is given by the circle modulus of z is equal to 1. Comparing this with the standard form, we have a circle which is centered at the origin and radius 1. Also, f of z given in the question can be written as z minus 3 divided by z square plus 2z plus 5 in the denominator can be written as product of z minus of minus 1 plus 2i and z minus of minus 1 minus 2i. To find the poles, equate the denominator to 0. So z is equal to minus 1 plus 2i and z is equal to minus 1 minus 2i are simple poles. Both the poles geometrically represented by the points minus 1, 2 and minus 1, minus 2 lie outside the given circle. To check whether the poles lie inside or outside the circle, we calculate their distance from the center of the circle. Here the center of the circle is 0, 0. For the point z is equal to minus 1 plus 2i, the distance is given by square root of minus 1 square plus 2 square, that will be root 5, which is greater than 1. Similarly, for the point z is equal to minus 1 minus 2I, distance will be square root of minus 1 square plus minus 2 square, that will again be root 5 and which will be greater than 1. So both the poles lie outside the given circle, therefore the function is analytic inside the circle. Hence by Cauchy's theorem, the given integral equal to 0. Consider part B of the same question. Here we are given modulus of z plus 1 minus I is equal to 2. Comparing this with the standard form, geometrically this represents a circle with center minus 1 comma 1 and radius 2. Again, f of z will be written as z minus 3 divided by the denominator will be written as the product of z minus of minus 1 plus 2I and z minus of minus 1 minus 2I, where z is equal to minus 1 plus 2I and minus 1 minus 2I will be the simple poles. To check whether the poles lie inside or outside the circle, let's calculate their distance from the center of the circle. For the pole z is equal to minus 1 plus 2I, the distance from the center is square root of minus 1 plus 1 whole square plus 2 minus 1 whole square, that will be 1, which is less than 2. That means the pole lie inside the given circle. Similarly, for the pole z is equal to minus 1 minus 2I, the distance from the center is square root of minus 1 plus 1 whole square plus minus 2 minus 1 whole square, which is 3, which is greater than 2, so it lies outside the given circle. So only one pole, that is z is equal to minus 1 plus 2I, lie inside the circle, which is a simple pole. So m will be equal to 1 and a will be equal to minus 1 plus 2I. Using the formula for residue at a simple pole and substituting these values, z minus of minus 1 plus 2I cancel out in the numerator and in the denominator, and we are left with limit as z tends to minus 1 plus 2I, z minus 3 by z plus 1 plus 2I. Applying limit, we get minus 1 plus 2I minus 3 by minus 1 plus 2I plus 1 plus 2I, which is 2I minus 4 by 4I. Separating both the terms, we get 1 by 2 plus I. By residue theorem, the given integral will be equal to 2 pi I into sum of residue of f of z at z is equal to minus 1 plus 2I. Substituting the value, we have 2 pi I into 1 by 2 plus I, which will be simplified as pi into I minus 2. Consider part C of the same question. Here we are given modulus of z plus 1 plus I is equal to 2. Comparing it with the standard form, we have center as minus 1 comma minus 1 and radius as 2. Again, from the previous parts, we know that z is equal to minus 1 plus 2I and minus 1 minus 2I are the simple poles. To check whether the poles lie inside or outside the given circle, calculate the distance of the pole from the center of the circle. The distance of the pole minus 1 plus 2I from the center is given by square root of minus 1 plus 1 whole square plus 2 plus 1 whole square, which is 3, which is greater than 2. That means this pole lie outside the given circle. For the pole minus 1 minus 2I, the distance is given by square root of minus 1 plus 1 whole square plus minus 2 plus 1 whole square, which is 1, which is less than 2. This pole lie inside the given circle. Calculating residue at this pole, we have m is equal to 1 and a is equal to minus 1 minus 2I. Using the residue formula for a simple pole, substituting the values, we get limit as z tends to minus 1 minus 2I, z minus 3 by z plus 1 minus 2I. Applying the limit, we have minus 1 minus 2I minus 3 by minus 1 minus 2I plus 1 minus 2I. Simplifying this, we get minus 2I minus 4 by minus 4I. Separating both the terms, we get 1 by 2 minus I. By residue theorem, the given integral is equal to 2 pi I into sum of residue at z is equal to minus 1 minus 2I. Substituting the value, we have 2 pi I into 1 by 2 minus I, which simplifies to pi into I plus 2.